Okay, something a little weird going on with my internet, but anyway, it seems to be okay at the moment. Okay, let's let everybody get in. Okay. So class attendance in both my first class and in Jerry's first class, and now in this class looks to be down. Not sure if it's just because the um, weather's too nice or what the deal is. But anyway, if no more people come, that's what I'll do in this class, what I did in my first class. Everybody gets 2 extra points on the final exam for showing up when almost nobody showed up. Okay. So homework questions. First of all, my lab, Pearson, my lab was down for scheduled maintenance, but it sort of interfered with some people trying to do the homework. So I extended some of the deadlines. So if you look, I emailed about that, but I extended one, I think 1 or 2 more of them today. Okay, so, all right. So we're doing Laplace transforms now. And so do you have questions?
Can we do 7.4 number 9?
Okay, now I think I have everything open to be able to see that. Let's see, almost everything. Okay. Okay, 7.4, number 9. Okay. One property of Laplace transform can be expressed in terms of the inverse Laplace transform. Okay, so this is, let's see, I'll go back to where I can see where I'm writing. Let me just copy the problem down first. The inverse Laplace transform of the nth derivative of the Laplace transform of f. So the inverse Laplace transform gives you back a function of t is -1 to the n f of t. Okay, so use this equation to compute the inverse Laplace transform of f, where the one I see is capital F of s is ln of s plus 9 over s plus 5. Okay. Okay. All right. And let me get back to the other screen so I can watch where I'm writing. Where is it? Okay. All right. Let's see, I can't find the whatchamacallit screen. Well, y'all let me know if I can't. Let me just start working on this. And if I go off screen, just speak out and let me know. Okay. All right. So first of all, we have to find the function whose Laplace transform. We need little f of t such that the Laplace transform of little f of t is capital F of s. Okay. All right, and so notice that you can write capital F of s as ln of s plus 9 minus ln of s plus 5, just by the properties of logarithms, okay? So if you differentiate capital F with respect to s, you get 1 over s plus 9 times the derivative of s plus 9 with respect to s, which is just 1, and then 1 over s plus 5, okay? And notice that the inverse Laplace transform of this guy Okay, that's a function of t. Let me emphasize that. So that is the inverse Laplace transform of 1 over s plus 9 minus 1 over s plus 5. And the inverse Laplace transform is linear because the Laplace transform is. So this is the inverse transform of 1 over s plus 9 minus the inverse transform of 1 over s plus 5. And if you look up s plus 9 in the table, you will get e to the minus 9t. And then it's minus, you just copy it down, it's linear. And then if you look up s plus 1 over s plus 5, you get e to the minus 5t. Okay. So that says that the inverse Laplace transform. Okay, so that's the inverse Laplace transform of the derivative of f. So that is the inverse Laplace transform of f of s then is minus 1 over, okay, so, sorry, let's see. All right, so we have this. So I did not copy that right, the thing in the homework problem. I did not copy that right. So let's see. This is minus t to the n. There you go. Okay. So I put minus 1 to the n. That's wrong. It's minus t to the n. Okay. So we computed the Laplace transform of the first derivative of f, and we got e to the minus 9t times e to the t. So the zeroth derivative then, or the inverse Laplace transform of f of s is going to be equal to minus 1 over t times e to the minus 9t minus e to the minus, what was it, 5t. Because we're taking in other words, you have to have the function so that when you take maybe this isn't the best notation in the world. If you think of this as the function, then when you take its first derivative, you have to get to this Laplace transform. Okay, so it's this one. Maybe let's do another one like that too. We can get a similar problem. These tend to be a little bit confusing. So let me go back to the MyLab homework and get another similar problem. Well, first, do you see what, well, oh, wait a minute. This was first derivative. Yeah, that's right. So because the first derivative has to be minus t times f, and we got just this part. Let me explain it that way. So the first derivative has to be just this part. And according to the line above, the first derivative as a function of t would be minus t to the 1 times f of t. So which function would have just e to the minus 9t times e to the minus 5t being minus 1t times the f? It's this one, because you need that minus 1t in front to cancel this factor so that you end up with just this first derivative. Is that clear? You're kind of working backwards and forwards. Let's try another one. Let's see, I think number 10 was also along those lines. It is. Okay, so let's do number 10 as well. Maybe see if 2 like that will make it more clear. So the rule is the same, so I don't have to rewrite down the rule. But now we have f of s is the arctangent of 10 over s. Okay, so you know you're going to want to differentiate that. So when you differentiate this guy, you get 1 over 1 plus 10 over S quantity squared. Okay, so that is 1 over 1 plus 100 over S squared. So that is S squared over S squared plus 100.
Can we
Okay.
also take the derivative of the
Oh,
inside?
yes, I got to multiply by that. Thank you. So this has to be times, that's 10s to the minus 1. Thank you. I forgot the chain rule. So this is minus 10s to the minus 2. Okay. So I have a minus 10s to the minus 2. So let's do that. So that means I'm multiplying the numerator by minus 10, and I'm multiplying the denominator by S squared. Okay. So this is minus 10 over S squared plus 100 squared. Okay. Okay. All right. So if you look up, so if you ask which function, let me call it G. Well, let's say, what is the inverse Laplace transform of 10 over S squared plus 100? Okay. If you look that up, you will get the sine of 10t. Okay, if I'm doing that correctly, I remember, I think sine is the one with the constant. I'm pretty sure that's correct. And we have a minus sign out in front. Okay, that's easy to keep track of. So now you need to know which function, and remember that the inverse Laplace transform of the first derivative will be minus t. Where's my rule? It'll be minus t to the first times f of t. So in other words, minus t times f of t is equal to sine 10t. Okay, so that says f of t has to be equal, is equal to minus, because there's a minus sign here. So this should be minus, because I'm interested in the one with the minus here, which would make a minus here. So I need minus t, f of t, to be minus sine 10t. So that says f of t has to be equal to 1 over t sine 10t. Okay. And maybe that would be the better way to explain this first one that I did. You see, we had, we computed the Laplace transform of the derivative. Okay, we got that one. So in other words, L inverse of the first derivative of f is equal to minus t times f of t. On the other hand, minus t times f of t is equal to e to the minus 9t minus e to the minus 5t. So f of t, little f of t, has to be equal to minus 1 over t e to the minus 9t minus e to the, this was a minus 5t. And maybe that's a better way to explain it than the way I explained it before. Okay. The f, the function you want, is given by this rule. You computed the Laplace transform of the derivative because that's the easy one. And then you have to use this rule to get back to the original function, little f, that you're looking for. Okay. So again, these Laplace transform things are, they're simple in one way because you have all the rules right in front of you, but they're not simple in another way because you have to do all the computation. I mean, the computations are non-trivial. It's not obvious sometimes. Okay. Okay. How about another one?
Could you do number 7 on the 7.4 homework?
Okay. Let me get back there. I just found the Chrome, the Zoom thing, and now I'll go back. So hopefully I'll find it again. I got a lot open on my desktop. Okay, you said number 7? Okay,
Yes, ma'am.
okay. These two out of the way. And let me copy it down. So for this one, capital F of S is 5s squared plus 88s plus 292. Ominous looking numbers, I'll tell you. Over s minus 2 times s squared plus 8s plus 41. Okay. Okay. All right, and I'll need to open the table of Laplace transforms. Okay. All right, so I'm going to go over where I can see, but I'm sure I'm going to have to come back to do the Laplace transforms, inverting it. Okay, so whenever you see something like this, you know you're going to have to do a partial fraction decomposition. Okay, so we're going to have to write this as 5, and my 5s and s's look suspiciously alike. 5s squared plus 88s plus 292 over s squared, s minus 2 times s squared plus 8s plus 41 is equal to a over s minus 2 plus bs plus c over s squared plus 8s plus 41. And notice 41's prime, so this does not factor. So we're going to have to play some games when we go to invert that one. But first of all, you have to get your partial fraction decomposition. Okay. All right, and so I multiply through by the denominator. Okay, so that will give me on the left-hand side, I'll get 5s squared plus 88s plus 292 is equal to a times, don't try to skimp on writing things out. These get messy and you need to see the stuff. Okay. All right, so now we need to expand this right-hand side. So we get as squared plus 8as plus 41a plus, new pen time. 41a. Oop. Bad choice of pens, perhaps. Okay. Yep, that one's out of ink too. Okay, hang on a second. So we're going to have a bs squared, but I need something that I can write with. Okay, so I get a plus bs squared minus 2bs plus minus cs plus 2c. Okay, so that means, let me be really careful. So the s squared terms are a plus b. That takes care of this and this. The s terms are 8a minus 2b minus c. So that's this, this, and this. And then my constant terms are 41a plus 2c. Okay. All right, so I have 3 unknowns, a, b, and c, and I have 3 things to match it up with. Perfect. So that says a plus b has to be equal to 5 because the coefficient of s squared on the left and right have to match. That's the whole idea of partial fractions. The s terms, that's 8a minus 2b minus c has to equal 88. Okay. And then the last term, the constant term, says 41a plus 2c has to equal 292. Yuck. Okay, so I don't know. Maybe let's get, let me do it this way. So I'm gonna say B is a minus 5. Okay, so I'm gonna write, this is 8A, and let's do this one too. C, or 2C, is 292 minus 41A. So C is 146 minus 41 over 2A. Okay. So now I'm going to plug both of those into this equation. Let me come down and give myself a little room. So this will be 8A minus 2 times B. So let's be careful. That'll give me a minus 10 and a plus 2A. And then minus C. So that will be minus 146 plus 41 over 2A, and that's equal to 88. So that's 10A, which is 20 over 2, plus 41 over 2 is 61 over 2 times A is equal to 88, and this is a minus 156, so on this side it becomes a 1 plus 156, which is 4 and 1 over 4 and 1 over 244. So that says A is 488 divided by 61. Yuck. Okay, but whatever it is, it is. Okay. All right, I think I did that arithmetic correctly. And now let's see, B is going to be 5 minus A. Oh, this is so much fun. Okay, 61 times 5. Let's see, that's 5 and nothing over. So that's 305 over 61 minus 488 over 61, which will be 183 over 61 with a negative sign. Okay. And then C is 146 minus 41 over 2 times A, which is lordy. Okay. Well, the 2 cancels and makes this a 244. Not really much better. Okay, so this is 146 times 61 minus 41 times 244, all over 61. And now it's time for a calculator. I promise you, you won't have numbers like this on the exam. So let's see, 146 times 61 is 906. 41 times 244 is 10,004. And you divide by 61. So 10,004 minus 80. What was that? 8906? I can't even read that writing. And then you divide by 61. 18. How about that? It's minus 18. Okay. And actually, this one is minus 3. I should have done that before. Okay. And this one is 8. Oh my goodness. Sometimes a calculator is handy. Okay. All right. So the coefficients work out to be not that bad. So we have 8 minus 3 and minus 18. Okay. So we go to here. Okay, so the inverse Laplace transform of our f. I'm not going to write it all out again. Let's see. A was minus 8. So that is the inverse Laplace transform of 8 times 1 over s minus 2. Plus, that one's going to be fairly easy to do. Plus the inverse Laplace transform of, let's see, what was what? B was -3 and C was -18. So that is -3s minus 18 over s squared plus 8s plus 41. Okay, this one's easy to look up. That first one is 8 times, let's see, let me look at the chart. If you look at 1 over s minus a, that's e to the at. So this is 8 times e to the 2t for this one. Okay. And this may or may not help. Let's see, half the coefficient of 8 is 4 and you square it. Yeah, it's not going to help. Okay. So now let's focus on how do you do this transform, and then we'll come back and fill it in at the end. Okay. All righty. So I'm going to take the minus sign out in front. So that is a 3s plus 18. We'll just put the minus sign in at the end. Okay, we're not going to carry that along. And then you have s squared plus 8s plus 41. Okay, notice you're not going to be able to do anything with that bottom because it doesn't factor. Let me get back to where I can see what I'm writing. It doesn't factor. So you have to complete, you have no choice but to complete the square in s. So that's a common trick on these things. You have to complete the square in s and get it to something that'll give you a shifted sine or cosine, most likely. Okay, so you take half the coefficient of s, that'll be 4. You square it, that'll be 16. So you put in a plus 16 here. That means you better take 16 off that 41 to compensate for that. Okay, so this is L inverse of 3s plus 18 over, this is s plus 4 quantity squared. And then this is 25. Okay. Okay, so that means I have, now this is sort of the messiest form that you can get on this. Now, you would like to do a sine or a cosine. The constant one is easy to adjust for to get the sine term. The cosine term is tricky. You can't get cosine if you look on your chart that they give you or the chart that they give you in the book. Let me write it in a different color so it'll stand out from this. On the chart, you have e to the at sine bt is b over s minus a squared plus b squared. Okay, and e to the at cosine bt is s minus a over s minus a squared plus b squared. Okay, the constant one, the sine one, you can always adjust for because the Laplace transform's linear. So you can move constants around. But to get the cosine one, you have to have s minus a in the top, not just any old thing. It can't be s or s minus something else. It has to be the same factor here has to be in the numerator. So when we go to this one, I have to think of that as, all right, I'm going to pull the 3 out of the way in the numerator. So this is 3 times the inverse Laplace transform of s plus 6 over s plus 4 squared plus 25. So I need an s plus 4, not an s plus 6. How do I compensate for that? How do I make up for that? I think of writing this as s plus 4 plus 2. And I'm going to group this together and think of that one separate. Okay. So now I can think of this as 3 times L inverse of, the 3 is going to be times all of it. I have an s plus 4 over s plus 4 squared plus 25 plus an L inverse of 2 over s plus 4 squared plus 25. Oh, okay. So you see, if you're bad with algebra, it's very hard to get this stuff right because it's a lot of steps. It's easy at, it's sort of the same thing all the time. There's only so many tricks they can do. But to make sure you can complete the square correctly, and then divvy up the numerator correctly. And then remember that when you add a fraction, the denominator stays the same. It's only that you add the numerators. That's what we did here. Okay. And the fact that the Laplace transform and its inverse is linear. Okay. So now we are to 3 times L inverse. Okay. So L inverse of this one, you can look up. It's using this term right here. You have A is -4. So this one becomes e to the -4t times cosine of 5t. Okay, so that one's okay. Now with this one, I need a 5 in here, not a 2. So I'm going to need to multiply by 5 on the inside, which means I have to put a 1/5 out in front to cancel it. Okay. And then I need to move that 2 out of the way. So I have 2/5 L inverse of 5 over S plus 4 squared plus 25. Okay. Okay, and now we're ready to use this one because I have a B squared, that is the 25, and then I have the 5 up top. So I can use that formula. So I have 3 times e to the -4t cosine 5t, and then I have 2/5 e to the -4t sine 5t. Okay. And so now we can go back to the top and put it all together. So L inverse of f of s is the part we found before, 8e to the 2t. And now we have a minus all of this thing, and we have to distribute the 3 because there was a minus sign in there. So this is -3 e to the -4t cosine 5t minus 6/5 e to the -4t sine 5t. Okay. So in principle, it's real easy. You got the chart. In practice, that's not so easy, right? There's a lot of calculations in between, a lot of algebra steps you have to remember and get correctly, or you go way off in the wrong direction. So I know y'all must have some questions about this. So where on the questions? If nobody's asking questions, you're not being honest. People always have questions on this stuff. No? Don't be shy. No one? Okay. How about another one? Another one in the homework?
Could you go over 7.5, number 4?
Sure. Let's see, let me get over to that. Okay, number 4. Okay. Yeah, okay, so now we're to the point. These are this kind of problems is to the point of solving of why we're doing all this Laplace transform business. And then pretty soon we'll be doing Laplace transform of impulse functions and things that we couldn't do by any other method. So this is 7.5, number 4. And your equation is 3t y double prime minus ty prime y prime plus y equals 6. And then you have y of 0 is equal to 6. And y prime of 0 is equal to -5. Okay. And we're going to need the table of both Laplace transforms and the properties of Laplace transforms. Okay. All right. Okay. So let's see. Let me try to get back to where
Is it 5 or -5?
-5. I have -5. You're right. Thank you. And I need to get my tables to show. They're showing one on top of each other, and that's not the best. Okay. Okay. All right. We want to look at this, and now we have to take, basically the idea is you take the Laplace transform on both sides of the equation, okay? So if you look at, so we want to take the Laplace transform of ty double prime minus ty prime plus y, and that's going to be equal to the Laplace transform of 6, okay? All right. When you do the Laplace transform of, sorry, let me see. Let me get back to where I can see. And now I got to get back to the chart. This is tedious going back and forth like this. Okay. All right. So if you look at the chart in the properties of Laplace transforms, line 1, 2, 3, 4, 5, 6, 7, with n equals 1, says the Laplace transform of t times f is equal to -1 to the n times well, with n equals 1, sorry. With n equals 1, I'm just doing that because all we have is a t times that things. So that will be -1 times the first derivative with respect to s of the Laplace transform of f. Okay. Okay, so we're going to let the Laplace transform a little y. We're going to call it capital Y. Okay. Okay, so now we apply, and the other thing we need is the Laplace transform for the derivative. So the Laplace transform of the derivative, the nth derivative of t, is going to be, it's s squared times the Laplace transform of f. I'll quit writing the arguments. Minus s times f of 0 minus f prime of 0. Well, this is a second derivative. Let me just do the second derivative, and then I'll do the first derivative as well, because that's the ones we're using. And likewise, the Laplace transform of f prime is s times the Laplace transform of f. Okay. Okay. All right. So all right. And let me get back to now, where was I on the screens? Okay. Okay. All right. So now we want to start applying the Laplace transform to our equation. Okay. So when we do this, so the Laplace transform of 6 is really easy. That's just 6 over s. So let me write that on the left-hand side. And that's an s. Okay. And now we want to take the Laplace transform of the second derivative. All right, we wrote down the derivative formulas. So we will have the Laplace transform Let me write some of these in stages. Yeah, maybe I need to write one more stage for you. So when I take the Laplace transform of y double prime, notice that is s squared y of s minus s times y of 0, which is 6, minus 6s, and then minus f prime at y prime at 0, so that will be a minus 5, so that'll be a plus 5, okay? And the Laplace transform of y prime is just going to be s times y of s minus y at 0, okay? So I get that, all right? All right, and now we have to use the first two lines of or this line of what I wrote down before. How do you take the Laplace transform of t times something? Okay, so what's the Laplace transform of t times y prime? Okay, that will be, according to the theorem, minus the derivative with respect to s of s. Okay, now I'm taking the derivative of y, the derivative with respect to x of the Laplace transform of y prime. So that is sy of s minus 6. Okay, so notice that is equal to minus s y prime minus minus y, and then the derivative of 6, that goes away. Okay, so I get minus sy prime minus y for t times the first derivative. What about when you take the Laplace transform of t times a second derivative? Okay, that's the derivative with respect to s with a minus sign of the Laplace transform of y double prime. That's this guy. Okay, so when I take minus the derivative of this, so the product rule on the first one, that will give me a minus s squared y prime minus 2sy, and then I'll get a plus 6, and then nothing from the last one, okay? So now we plug those equations into our original equation, the Laplace transform of ty double prime minus the Laplace transform of ty prime plus the Laplace transform of y is the Laplace transform of 6. Okay, so, okay, so let me get back, okay. All right, so when I plug into, maybe it's hard to fit it all. Okay. So Laplace transform of ty prime, that will give me a minus s squared y prime minus 2s y plus 6 minus the Laplace transform of ty prime. So minus this thing. So that will be a plus sy prime plus y plus the Laplace transform of y plus y is the Laplace transform of 6, which from the chart is 6 over s, if I remember correctly. Yes, okay, all right. So now let's gather up our terms with the derivatives and the y's and see what we have, okay? So I'm gonna, so I have a minus s squared plus s times y prime. So I can see what I'm writing. And then, so that's these two terms. And then I have a minus 2s and a plus 2y. So minus, okay, minus 2s minus 2 times y. Okay, so that's this term and these two terms. And then I have a 6 over here. I'm going to bring that to the other side. Okay, and now let's go ahead and divide through by this coefficient, So I get y prime. There's a minus, I'll make this a plus 2 times s minus 1 over, I'm taking out a minus sign. This will be an s times, well, let me just write it as s squared minus s. So I'm dividing by minus s squared plus s, but there's a minus sign and I factor out a minus sign from the denominator. I factored out a 2 while I was at it in the numerator. And this is 6s minus 6. Okay. And now you notice this is a linear equation. Linear first order equation for capital Y. We know how to solve linear first order equations. Do the integrating factor and all that thing. Okay, so let's do that. Okay. So now when you do the integrating factor is going to be, it's going to be the integral of 2 times s minus 1 over s squared minus s.
Professor,
Uh-huh.
you forgot to put the 3 in the first part.
Where was the 3? Oh my goodness. Oh, drats. Okay. Yes, it's a 3. I left it off at the very first line. That's why I forgot it. So let's see. That makes us have a 3 times the second derivative terms, which is this one. And then this will be a 6s. And then it will be an 18. Okay, that's going to make a big change. So let's see. That gives me a minus 3s squared. And now I have, this is a minus 6s. And then it's still minus 2. That's correct. Okay, and then on the other side, it is a minus 18. Thanks for not letting me go on. It might have gotten worse. Okay, so that makes this a 6 and a 3s squared. Okay. 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 Well, that looks like that's going to make this a lot of fun to integrate. Okay. So we have a 6. Okay, so now let's scratch that. Let's just start that over. So the integrating factor here is going to be 6 times the integral of s minus 1 over 3s squared minus s ds. Well, that's not the integrating factor. That's the integral of rho, and then the integrating p rather, and the integrating factor is this. So we have to work on this a bit. Okay, so let's see. That looks like it's going to be a partial fraction. I cannot see. Well, let's see. It's a 6s minus 1. Did I do the factoring right here? Let's see. Maybe I didn't. When I put that 6 in, that gives me a 6s times y. And then a 2, yeah. This is a 6s minus 2. Yeah, so I didn't, this is not quite right because that factor changed. So this is, let's just leave it as 6s minus 2. So this becomes 6s minus 2. Okay, so this becomes 6s minus 2. Okay, you have to make the change. If you make an error, you have to correct it correctly. And I almost botched it there. Okay. All right, so let's see. When you do this, this is a 6. If you let, yeah, that's not going to be any better. Too bad. Too bad. Okay. All right, I guess we have to do a partial fraction decomposition. It doesn't look like you're going to be able to do anything better than that. So you write this as s times 3s minus 1 over 6s minus 2. So that's A over S plus B over 3S minus 1. Okay, so now when we multiply through, we get 6S minus 2 is A times 3S minus 1 plus BS. Okay, so we have 3AS minus A plus BS. Okay, so that's S times 3A plus B minus A. Okay, so that says A minus A is minus 2, so A is 2. And 3A plus B equals 6, and A is 2, so that says B is 0. Okay. That can't be right. All right, something is amiss here. What did I do wrong now? Three AS minus A plus BS, 3A plus B is 6, and minus A is minus, oh, minus A, yeah, no, minus A is minus 2, so A is 2. Oh, duh. Oh, my goodness. Okay. Well, that's a real brain blip. Look. Oh, my goodness. Okay. So when you factor out, so if you factor out a 2, duh, you get 3S minus 1 in the numerator over S times 3S minus 1, duh. So that's 2 over S. So that was really the long way to get to that simplification. Okay, that pen's out of ink. Let me grab another one. Let's try this one. Okay. Okay, so B is 0 and A is 2, but man, that was a long way to get there. Okay, so the integral of the what we would call P in this, 6S minus 2 over 3S, is just the integral of 2 over S ds, which is 2 ln absolute value of S. And so e to the integral 2 over S ds is e to the 2 ln absolute value of S, which is e to the ln S squared. So that is S squared. Okay. All right. So now we go back to our equation for Y. And remember, the coefficient here is just 2 over S. Okay. So now you multiply by S squared. So you have S squared Y plus 2 over S times S squared, which is 2SY, is equal to S squared times this left-hand side. So that will give me a 6S minus 18S squared. Okay. Okay, and notice that this is the perfect derivative of S squared Y. Okay, so now you multiply by ds and integrate. So that says S squared capital Y is equal to, okay, that's 6S squared divided by 2. So that's 3S squared. And then you get minus 6S cubed plus C. And now you divide by S squared. And so finally you get Y of S is 3 minus 6S plus C over S squared. Okay. Okay. Okay, so what that did is that solved, we're not done yet, but that solved the ODE and took care of the initial conditions all at the same time. So now all that's left to do is to invert this guy to go back, because you had a differential equation in terms of Y and T. You can't give your answer in terms of the Laplace transform of Y and S. So now we have to invert. So the inverse Laplace transform is linear. So that means we have to invert 3 terms. I'm sorry, let's see, we have a plus a C. And let's see, to deal with that plus C, we have to use the initial condition. So I'm not quite ready to do this yet. Let's do the initial condition. So we have y of s is 3 minus 6s plus 6 over s squared. Okay. So the initial condition says that the Laplace, we had y, y prime of 0. Well, let me go ahead and invert first, and then I'll worry about getting that c. I'm going to do it that way. Okay. All right, so I'm going to go ahead and do the inverse of Laplace transform of y. So this is 3 times, or the inverse Laplace transform of 3, if you like, or 3 times 1. 1 is the one you look up on the table, minus 6 times the inverse Laplace transform of s, plus c times the inverse Laplace transform of 1 over s squared. Okay. Okay, now when you look up the inverse Laplace transform of S, okay, let me get back to my Laplace transform charts. Oh, they disappeared. Okay, here they are. Okay, so the first one is trivial because in the chart, if you look up the constant, well, if you look up, they don't have that one listed. Okay, so you should have a different Laplace transform chart. Let me get my other chart out. Okay, let me. Okay. We should have a big Laplace transform chart in the book. Well, if they don't, we're going to have to do this the hard way. Okay. Okay. All right. So the only easy, so we have 2 of them that are a bit of a pain. So we have to do the inverse Laplace transform of 1 over s squared is really easy because if you look up in the 3rd row of the table of Laplace transforms with n equals 1, this gives you t. So this one inverts to 1 c over t. Okay, so that's the inverse of that one. What about the inverse Laplace transform of a constant? Okay, so that's not listed anywhere. So you're going to have to figure out a creative way to do that. Okay, so let me think about that one. That's an unusual one. I'm just wondering if I made a mistake somewhere along the line. Okay, I'm just, well, so give it, I'm assuming that I didn't make a mistake. So we have to look up the inverse Laplace transform of this, and we have to compute the inverse Laplace transform of S. So the inverse Laplace transform of S, you can do by looking at, okay, I got to get my other table to open too. Okay, let's try to be creative on this one. And this is not 1 over t, sorry, this is c times t. Okay. And inverse Laplace, you don't usually see this. So let me double check what I did in these calculations and make sure I'm not off track. Because if you make a mistake, you'll get something that you can't do. Okay, so we got the equation and we got down to our ODE. Let's see, where was the other sheet? Okay, so our ODE is y prime plus 2 over sy is equal to 6 over s minus 18 . Okay, and oh, I see. I did. Okay, there is a mistake here. Let's go back. And I think basically by making that mistake in the constants, by forgetting that -3, I threw things off again. So let's restart from here. So this is -3y squared, 3s squared y prime. And then I have a minus 6s plus 2. So if I put the minus sign outside, it's a -2 times y is equal to, I have an 18 here. And so that goes to the other side. So that is 6 minus 18s over s. Okay, and now I'm going to divide by 1 over s, divide by -3 over s. Sorry, this is not even right yet. I have a plus s squared. Plus s. That's this one. Okay. That was this one. Okay. So I have this. Okay. So now I need to divide by this term. So that will give me a y prime. This, I'm dividing by minus 3s squared minus s. Okay. So the minus and the minus will give me a plus. That is a 2 times 3s minus 1. And then this is an s times 3s minus 1. And I'm dividing by a minus, so this gives me a minus. And factoring out a 6 here. And I'm factoring out a minus. This gives me 3s minus 1. I'm dividing by a minus. That'll make it a plus. And then I have s times s, 3s minus 1. So you get a lot of cancellations. Okay, so I had the equation wrong. That's why I was getting something I can't invert. So this, and I left off my y here. So the 3s minus 1 cancels here. The 3s minus 1 cancels here. So your ODE, the linear ODE for capital Y is just this. Okay, that's a lot simpler. And this is an S, not a 5. Okay, so now your integrating factor is e to the 2 over s ds, which we worked out before. That's s squared. That integrating factor didn't change. So I multiply both sides of the equation by s squared. It gives me a 6s. Okay. All right. And now, now this is the derivative with respect to s of s squared y is equal to 6s ds. Integrate on both sides. That gives you s squared capital Y is equal to 6s squared over 2. But something again is amiss. What did I do wrong? Something is very strange because I'm getting 6s squared over 2, so that's a 3s squared plus c. So I'm again getting a constant. So y is 3 plus c over s squared. And that is the problem. You can't invert a constant. So I am making some kind of crazy mistake over and over. I am not sure what I'm doing, but you shouldn't have a constant here. I know that much because you can't invert just a constant. Laplace transform equal to a constant is not an invertible thing. All right, let's look one more time at this really carefully and make sure I'm not doing some kind of sloppy algebra. Start again. Okay, so we take taking 3t y double prime, and you're taking the Laplace transform of that. So I'm multiplying this by 3. That gives me a minus 3 s squared y prime plus 6 sy plus I'm multiplying by minus 3. So that gives me a minus 18. No, I'm just multiplying by 3. Sorry, I'm multiplying this by 3. That's a plus 18. Okay. And now I take minus t times y prime. So I minus this thing. That gives me a plus sy prime plus y. And then I add to that the Laplace transform of y. And that should be the Laplace transform of 6. And the Laplace transform of 6, let's just be real careful. The Laplace transform of 6 is 6 over s. Okay. All right, so that gives me a minus 3s squared minus s times y prime plus 6s plus 2y. Okay, and then I have 6 over s minus 18. Okay. All right, and let's see, that gives, so I think of this as minus s times 3s minus 1. And I think of this as 2 times 3s plus 1. Sorry, something's wrong here. There should be a minus somewhere. This is a minus 3s squared. This is a minus 6s. There we go. So this is a minus 3s minus 1. Okay. And then this should be 6 over s minus 18. Okay. All right. And now I'm going to, and so let me write that as 6 minus 18s over s. Okay. Which I can also write as 3 minus 3 times, minus 6 times 3s minus 1. Okay. Over s. And now I'm going to divide by minus 3s minus, I'm going to divide by s minus s 3s minus 1. And don't forget the y prime. Okay, so the minus and the minus gives this. And I get a 2 over s times y. Okay, and now I'm dividing by the 3s minus 1, that cancels. Dividing by the s, I see, there's where my mistake was. When I divide by s times 3s minus 1, I get a, and a minus sign, I get a 6 over s squared. And there was my mistake. Okay. Dividing by the minus, that changes to minus. Dividing by the s, that makes that an s squared. Dividing by the 3s minus 1, that cancels those two. Okay, so now e to the integral 2 over s ds, that's a linear equation. Here's my integrating factor, that's s squared. So we have s squared times y prime plus 2sy is equal to 6. There we go. So this is s squared y, the derivative of that with respect to s is equal to 6ds. And so now we integrate both sides. Now it is. So you get s squared y, and that's equal to 6s plus c, finally. So y of s is dividing by y squared, 6 over s. There we go. That works. Plus c over s squared. There is no Laplace, inverse Laplace transform of just a constant. Okay, so there had to be a mistake somewhere, and it was in the algebra. Okay, so now we want to invert y of s. So we take the inverse Laplace transform of capital Y of s. That will give us little y of t up to this constant. Okay, so that means I take the inverse Laplace transform of 6 over s plus c times the inverse Laplace transform of 1 over s squared. And I can think of this as 1 over s with a 6 out in front. If you take the inverse Laplace transform of 1 over s, you get back 1. So this is 6 times 1. Okay. And then here you get plus c times the inverse Laplace transform of 1 over s squared is t. That's from the chart, reading from right to left. Okay. So now you know that y of t is this. Okay. So we know that y of 0 equals 6, but that's obvious from this. That doesn't tell us anything. When you put t equals 0, you get y is 6. So what about y prime? Well, y prime is c. On the other hand, by the initial condition, y prime at 0 was minus 5, so c is minus 5. So finally, I made that look a lot harder than it had to because I forgot the 3 and then messed up the algebra. Okay, all right. So you just have to be really careful on these things, and dropping constants is deadly sometimes. But the twist on this one was that your equation had a t in front of it. When it's constant coefficients, those are much easier. So let me do an example of one where there's a constant coefficient. Let's see if I can get one that's not too hopefully not too long. Okay. Here, let's try. This is number 1, actually, because I want to be able to finish it in the time. So when you have constant coefficients, they work out a lot quicker. So this is 7.5, number 1. Okay. So you have y double prime plus 7y prime plus 12y is equal to 100 e to the t. And y of 0 is minus 5. And y prime at 0 is 39. Okay. All right. So now you take the Laplace transform of both sides of the equation. Okay. All right. All right. So when you do that now, you take the Laplace transform of the second derivative, you get s squared times the Laplace transform minus s times y of 0 minus y prime at 0. Okay, and now we have to do minus 7 times the Laplace transform of y prime, which is s times the Laplace transform of y minus y at 0. And then you
Plus
have
7.
plus
And then plus
7.
7.
Yep. Okay. Man, I'm just batting 1,000 today. Okay, but this is still a minus sign right here. And then we have plus 12 times capital Y is equal to 100 times the Laplace transform of e to the t, which I don't have that chart in front of me, and I hate to flip back, but maybe here. Okay, here I have it. The Laplace transform of e to the t is 1 over s minus 1. Okay. So now you plug in your initial values. This one is minus 5. Here you have 39. This one is minus 5. So we have s squared y of s. Then we have plus 5s minus 39 plus 7s times y minus, so this is a plus 5 times 7 is plus 35 plus 12y is equal to 100 over s minus 1. Okay, so now gathering up our y of s, we have s squared plus 7s plus 12 all times y is equal to 100 over s minus 1 minus 5s my plus 39 minus 39 and a plus 35 is a minus 4, so it becomes a plus 4 on the other side. Okay. Okay, and so y of s now is 100. This may not be quite so trivial, over s minus 1 times s squared plus 7s plus 12. Okay. Minus 5 over s plus, well, it depends on how you want to write it. Let me write it like this. I'm probably going to have to do it in 2 pieces. Okay. Okay. So let's see, does this factor? If you did 4 and 3, that would give you 7 and 12. So this does factor. The denominator factors to s plus 4 times s plus 3. Okay. Okay. All right, so I guess you do have to do partial fraction decomposition. Oh, well, you might want to combine. Oh, no, you can't combine those two. Okay. So I guess you have to do partial fraction decompositions. Well, let's go ahead and do that. Okay. So let's save some space so we can come back and write our answer. But if we, let's forget the 100. We will just do 1 over s minus 1, s plus 4, s plus 3. That's a over s minus 1 plus b over s plus 4 plus c over s plus 3. Okay. Okay. So if you look at this one, so now let's do this as, I don't know, I guess just go ahead. So this is a s plus 4 times s minus 3 you have written out up here. So this is a times s squared plus 7s plus 12. And now you have b times s minus 1 times s plus 3. And then c times s minus 1 times s plus 4. So this is a(s) squared plus 7a(s) plus 12a if you work this one out, let's see, you get s squared minus s plus 3s. So that is s squared plus 2s minus 3. And this one is s squared plus 3s minus 4. You get plus bs squared plus 2bs minus 3b plus cs squared plus 3cs minus 4c. Okay. And so that says a plus b plus c equals 0. That's the coefficients of s squared. The coefficients of s says 7a plus 2b plus 3c equals 0. And then the last one is 12a minus 3b minus 4c equals 1. Okay. So A is minus B minus C. So this, not a lot of fun to do this, but let's see, another way you could do this is multiply this equation by 7 and subtract. And when I subtract, I get minus 5b minus 4c equals 0. So 5b plus 4c equals 0. And another way to do this one, I want to get rid of a, so I'll multiply this equation by 12 and then subtract. And when I subtract, I will get minus 15b minus 16c equals 1. So that says 15b plus 16c equals 1. So if I multiply this first equation by 3, that will become 15b plus 12c equals 0. Subtract, and that will give me 4c equals 1. So c is a fourth. Okay, and then you get the idea. So you get 5b plus 1 equals 0. So b is minus 1/5. And b plus c, oh, just for added fun. Okay, so a is minus b minus c. So that is 4/20 minus 5/20. So that is minus 1/20. Okay, so you invert that Laplace transform of the first one. By taking a was minus 1/20 times the inverse Laplace transform of 1 over s minus 1. And then b is minus 1/5 times the inverse Laplace transform of 1 over s plus 7. And then we have 1/4 the inverse Laplace transform of 1 over s plus 3, which I believe is 1 over, so this will be equal to minus 1 over 20 e to the t minus 1 over 5 e to the minus 7t. And then this is 1/4 e to the minus 3t. Okay, so that's the inverse Laplace transform for this first one, except you must multiply by 100. And now for the second one, you have to do the same sort of thing. You have to do a partial fraction decomposition. And then, okay, the last part of the problem, what we have to do is we have to go back and find the Laplace transform of 5, or the inverse Laplace transform rather, of 5s minus 4 over this denominator. Okay, so let's look at, we just found in class, we found the Laplace transform this one. So I'm tacking on the piece to find the inverse Laplace transform of this one. Now we're going to do that one. Okay, so we need to compute the inverse Laplace transform of 5s minus 4 over s squared plus 7s plus 12. Okay. All right. So notice that it's going to be a partial fraction decomposition. So this denominator factors as it did before to s plus 4, s plus 3. And then the numerator is 5s minus 4. So we want to write that as a over a over s plus 4 plus b over s plus 3. Okay. So that is multiplying through by the denominator. 5s minus 4 is equal to a times s plus 3 plus b times s plus 4. So that is on the right-hand side, as plus 3a plus bs plus 4b. So that is s times a plus b. And then the constant is 3a plus 4b. And that's equal to 5s minus 4. So that tells us that a plus b is equal to 5, and 3a plus 4b is minus 4. So use different ways you can solve it. Let's multiply this equation by 3 and then subtract. So multiplying this equation by 3 will give me 3a plus 3b is equal to 15. Okay, and now I'm going to subtract. And let's see that I subtract, the 3a's will cancel. I'll get 4b minus 3b, so that's just b. I have minus 4 minus 15 is minus 19. And since a plus b is 5 and b is minus 19, then a is 24. Okay, so we can write this expression that we want to find the inverse Laplace transform of. We want to find the inverse Laplace transform of this expression. And so using this decomposition, we're going to have 24. So I'm going to put the 24 out in front because the inverse Laplace transform is linear, times 1 over s plus 4. And then b is minus 19. So I'll put that minus 19 out in front, times the inverse Laplace transform of 1 over s plus 3. And if you look up s minus a in the table, you get e to the at. And so this is going to be 24 e to the minus 4t minus 19 e to the minus 3t. Okay. So now we put all that together. We had from earlier, we had y of s is 100, capital Y of s, over s minus 1, s plus 4, s plus 3, minus 5s minus 4 over s plus 4, s plus 3. Okay, and so our solution, little y of t, is the inverse Laplace transform, capital Y of s. So that is 100 times the inverse Laplace transform of 1 over s minus 1, s plus 4, s plus 3, minus the inverse Laplace transform of 5s minus 4 over s plus 4, s plus 3. Okay. So as we found earlier, the inverse Laplace transform of this one, the inverse Laplace transform of this one, in class I wrote a minus 7 at the end. This should have been a 4 because this is a 4 in the factorization. So this is e to the minus 4t. Okay. So the inverse Laplace transform of this term, let's see if I can get it where you can see it. So now I have to take 100 times that. So that is minus 1 over 20 e to the t minus 1/5 to the minus 4t plus 1/4 to the minus 3t minus the Laplace transform of the fraction we just found, the term we just found. And here's the one that we just found. So we have to subtract this. So this is minus 24 to the minus 4t plus 19 to the minus 3t, because you had to subtract that inverse Laplace transform. Okay, so now let's see. We can do a little combining here. So this is 100 divided by 20 is 5, and there's a minus sign. So that's minus 5 to the t. Then it is minus 20 to the minus 4t, and then minus 24. So I believe that is minus 44 to the minus 4t. And then this is 25 to the minus 3t plus 19. So 25 and 19 is 44. Right? Yep, that's right. To the minus 3t. So there is your solution. Okay. So most of the time, the inverse Laplace transforms are either straight from the tables, or a lot of times you have to do partial fraction decomposition. In a couple of lectures, we're going to learn something about inverse Laplace transforms of products. But first, we have to introduce the notion of convolutions. So that'll give us another notion. But basically, it's those three kinds of tricks. There are some fancier ones with derivatives and stuff, but these are the more standard ones. Okay, so these are the ones I really want you to master. Okay, so I hope that helps. We'll have plenty of time on Wednesday to do more problems. Okay, so be working on your homework. Bye.